Good morning again. So I'm starting off with chapter 21 material, where we're moving on. We're still dealing with carbonyls again, but now we're flipping this around. We're thinking about carbonyls as nucleophiles, as our source of electron density. Now that's important because every previous time we've looked at a carbonyl and we've said, the carbonyl carbon, this center right here, it's electron deficient, it's electrophilic, it would love to be able to react with some sort of nucleophile, some sort of electron density. But in point of fact, this carbonyl form, this electrophilic form, is actually in equilibrium with our nucleophilic form. It's in equilibrium with something that we call an enol. Now we've seen enols before. We've talked very briefly about them, in which we've got an alcohol and then an alkene here in between what was the carbonyl carbon and then an adjacent carbon, or what we call the alpha carbon. So you'll hear that term a lot, the alpha carbon. And let me go ahead and label that in here, the alpha carbon. Now this alpha carbon is actually nucleophilic because we have a resonance contributor for our enol in which we've taken that electron density in the alkene part and put it onto carbon, creating an electron-rich anion here, and then using lone pairs from our oxygen to help stabilize the cationic portion here. So we could actually put a third resonance contributor in here as well. But all of this makes this alpha carbon nucleophilic. Now we actually have a second option here too that I'm going to put down here, and this is the fact that we can start with our same carbonyl, and if we think about now the hydrogen atoms on this alpha carbon, so next door to our carbonyl, that we can have a base come along. Right at the moment it's going to be a generic base. Remove that alpha hydrogen, or alpha proton, generating an anion that's next door to our carbonyl. This anion is actually fairly stable, or considerably stabilized anyway, in that we can take and actually delocalize it such that that anion is partially on carbon and partially on oxygen. So it's spread out over all three of these atoms. More delocalized charge means it's actually easier to remove this proton than you might expect. And indeed, the pKa for a hydrogen next door to an aldehyde or a carbonyl is somewhere in the ballpark of right about 20. We'll learn that there are some differences there as we go along, but for now, right about 20. And we'll talk about the implications of that and equilibria. Do we get mostly enolate? Do we have mostly carbonyl in a subsequent little section here? But for right now, we have our enol option as a nucleophile, and then we have down here the enolate, that 8 part indicating we have a negative charge. We have an anionic species here. And so this is what we're going to introduce in this chapter, talk about, and actually carry on into chapter 22.